All right. Can everyone hear me in the back? Okay, great. Thanks. Hi, everyone. My name is Haowen Zhang, and currently I'm still at Arizona, but right after this conference, I'll be moving to CETA for my postdoc. So firstly, big thanks to the organizers, especially Avishai, for inviting me again. And it's always a pleasure to be able to present my science here. And firstly, and also I do apologize for changing the title a bit because I realize that every different group perhaps have their own definition for little red dots. So I guess for the sake of accuracy, I'll just say low luminosity AGNs, although a significant fraction of our sample are actually little red dots with broad emission lines. Okay, so today what I want to talk about is what we can learn from the abundance and clustering of low luminosity AGNs from JWST within the framework of Trinity. So we all know that JWST has been amazing, not only in terms of pushing the redshift frontier of galaxies and AGNs, but also, okay, feedback. Oh, okay, gotcha. But also, at slightly lower redshift range, like cosmic morning or redshift 3 to 6, JWST has really helped us push down the luminosity. Okay, push down the luminosity and black hole mass range that we're able to detect. So comparing these contours from, say, SDSS and JWST right here, we can see that we are basically talking about black holes or AGNs that are 100 times fainter and 100 times smaller in their luminosities and masses. And all those data have made it possible to measure not only the one-point statistics, for example, the AGN black hole mass functions measured by Anthony Taylor using the Sears data, but also very recently two-point statistics like the cross-correlation function between low luminosity AGNs and galaxies. And this work is led by one of my collaborators, Xiaojing Lin at Tsinghua University. And of course, from lots of imaging, we also found these little red dots. And these are, I think, the sample of little red dots that we found in the Congress sample. And all of them do come with broad emission lines. And in the talk, whenever I'm mentioning little red dots, I do mention the subset of low luminosity AGNs. Okay, so the question today is, what can we learn from the abundance and clustering of these JWST low luminosity AGNs within the framework of empirical models like Trinity? So for those who are less familiar, empirical models is a more flexible way to model galaxy and black hole evolution than hydrodynamical simulations and semi-analytical models, or SAMs. So we know that typically hydro simulations or SAMs have to assume some subgrid physics when modeling the interaction between galaxies and black holes. And although different simulations may use the same low redshift data set to calibrate their physics, their parameters in those subgrid physics, they usually produce very divergent predictions in the early universe where such physics are not calibrated. So empirical models take a different approach. Instead of assuming any specific physical mechanisms, empirical models would parameterize the connection between halos, galaxies, and black holes using flexible functions and constrain these empirical relations with observational data of galaxy and AGN directly. So by construction, our predictions of, for example, black hole mass versus galaxy mass relation will match all the observed data by construction. And with our results that is directly constrained by the data, we can actually use it to examine the predictions of all the different simulations with different subgrid physics And with this exercise, we can figure out which of these simulations would produce the scaling relations that are consistent with the constraints from observed data, and thus are more likely to be realistic. And really, we can do this exercise not only for just hydrodynamical simulations, but also for any theoretical model, as long as they can give us some comparable results with Trinity. For example, the abundance or clustering of low luminosity AGNs. So empirical models are flexible, but it also entails a lot of data to be included so that we can break the degeneracies between all the physical parameters. And one of these examples is the degeneracy between the black hole accretion rate and AGN efficiency. Because at the end of the day, what we're directly observing are AGN luminosities. And at a fixed luminosity, we can always get a higher black hole accretion rate coupled with a low efficiency or the opposite. But fortunately, we not only measure AGN luminosities, but also black hole mass at different redshift. So by combining all these different data jointly, we can break the degeneracy and solve for the AGN efficiency. So this is actually very similar to what we do in constraining the parameters of lambda CDM. So instead of using individual data sets that are super degenerate in this omega matter versus omega lambda plane, we use them jointly to get much tighter constraints for both of the parameters. And I guess the only major difference between Trinity and this lambda CDM exercise is that, firstly, we're using very different data sets. We are not only using the mass connections between galaxies and black holes, but also the quasar luminosity distributions in different galaxies across the redshift range. And the parameters that we're trying to constrain are the amount of black hole growth in different galaxies, as well as the AGN radiative efficiency. Okay, so basically we start with dark matter halo statistics from n-body simulations. And then we populate dark matter halos with galaxies with parameterized empirical scaling relations between galaxies and halos. And we use MCMC to make sure that by construction, such scaling relations would give us a galaxy catalog that will match all the galaxy mass functions or star formation rates, every galaxy data point that we input. And for black holes, we just do a very similar thing. We still use empirical scaling relations. And on top of the galaxy data, we also require that the model should match AGN luminosities in different galaxies at the same time. Okay, but there's this classic degeneracy between black hole accretion rate and efficiency. So we also need to make the model match the black hole mass functions or the black hole mass versus galaxy mass relations at redshift 0, and also AGN black hole mass functions at higher redshifts to figure out how much mass has been accumulated during black hole growth in different galaxies and how much AGN energy has been output during this process. And doing this, we can solve for the AGN efficiency and then convert the AGN luminosity or energy history into the mass accretion history. Okay, so now with this exercise, we have got a mock universe with a connection, with the best fitting connection between galaxies and black holes. So what can we learn from the abundance and clustering of JWST low luminosity AGNs with this model? So here I'm showing in navy data points the active black hole mass functions traced by AGNs in the Sears field. And all these different lines in different colors and line styles are different theoretical predictions. So it seems to be a good fit until you find that these data points are the active black hole mass functions from JWST. Namely, they only contain AGNs. But all these theoretical predictions, they are total black hole mass functions. In other words, they include not only AGNs, but also dormant black holes, and including Trinity. So if we were to make a real fair comparison between Trinity and Sears, then we should be comparing this yellow dotted line with the data points, which is the real active black hole mass functions from Trinity. So there's a factor of 30 difference between my prediction and Sears observations. But on the other hand, if we look at the clustering of these JWST low luminosity AGNs, we found that actually Trinity is matching the observation pretty well, at least in this Congress field. So apparently the problem is that Trinity underpredicts the abundance of low luminosity AGNs, but somehow matches the clustering. So how should we populate galaxies or halos with black hole differently to fix this problem? I think I have some naive solutions. Firstly, to fix the abundance issue, you could increase the typical black hole mass in low mass halos, or you can increase the scatter around the black hole mass versus galaxy mass relation for these galaxies, so that due to Eddington bias, you would boost the number of lower mass black holes to fill out the gap. You can also make these low mass halos more likely to host active black holes. In other words, you make these black holes growing more often so that you can be more likely to see them in observations. But the problem is that this will also lower the typical halo mass for these low luminosity AGNs. And because we do not have assembly bias accounted for in Trinity, the clustering of galaxies and halos are totally determined by their host halo mass. So the net result of this is that we will instead weakening, we will end up weakening the clustering of low luminosity AGNs in Trinity. So if we really want to make low luminosity AGNs more abundant while preserving their clustering signal, maybe we need to put them in certain halo populations with higher clustering signals at the fixed mass. In other words, we have to find some solution in assembly bias. And so for this purpose, since we do not have assembly bias in Trinity, we really need a new model beyond that. So in the next 3 years, I will be, I guess, in Canada building this black hole model, black hole empirical model of their histories, or behemoth. And the idea of this model is that in addition to the dependence on galaxy or halo mass, I'm going to use existing data of AGN properties in different galaxy subpopulations. For example, star-forming versus quiescent galaxies, and also like central versus satellite galaxies, galaxies in pairs or not, to figure out the typical black hole growth history and properties in all these different galaxy subpopulations. And hopefully, this model will help us find the right population of halos to host these low luminosity AGNs. So I guess in the interest of time, I'll just leave my summary here. And thank you so much. I would like to take any questions or comments.
Thank you. Okay, folks seem to be having a little bit of trouble connecting. So if I could ask the next speaker to come up and get your talk connected up while we get a couple questions here for him. See Phil all the way in the back.
All right. So just a clarification, I was a
Yeah.
little confused why, is it because there's a mass dependence in the duty cycle? I didn't understand why increasing the duty cycle would decrease the clustering. If it was just a uniform boost in the duty cycle, I would have assumed it preserves the clustering.
Right. So I guess, yeah, I should have been clearer about that point. So by duty cycle, I mean the duty cycle among the low mass halos only. So yeah, if you increase the duty cycle uniformly across the mass spectrum, then yeah, definitely you would preserve the clustering. But currently in Trinity, the AGN duty cycle among low mass halos or galaxies are really low. So if we can, I mean, naively, if we were to boost that only, then it would definitely make them more common. Yeah.
Okay, maybe one more question here. Yep.
Thank you for the talk. Is it possible to extend Trinity to even higher redshifts, maybe extrapolate to get, I guess, what the origins of these low mass AGNs or LRDs are, or is that not too trustworthy at this moment?
Sorry, so are you saying that is it possible to extrapolate
Yeah.
the results from Trinity to higher redshifts for what purpose?
But I guess like finding out where these like low mass AGNs, the halos or the star formation histories of these systems at the earliest times possibly.
So in principle, yes. So this is at the end of the day a mathematical tool. You can always do the extrapolation to as much as you want, but whether you can be confident of the result, I think it's up to your interpretation.
Okay, thank you. Let's move on to the next speaker.